All right, there we go. Worked around all the obstacles. Okay, Desmos. It's not working for some of y'all. A student in the last class said that he just closed the web browser and reloaded Desmos and then it worked for him. Right? I know some of y'all are logged in and it's like treating you as the teacher instead of the student. So I don't know if y'all tried that. So give that a try. I'll talk to the other teachers later today. See what the hell. Yeah, just try closing the web browser and reloading it. I think it's a Desmos thing as opposed to a me thing, but I don't know for sure, right? How many of y'all logged into Desmos okay? One. The rest of y'all tried and it wouldn't work? Yeah? Okay. So, yeah, a handful of people who it works for and then a whole lot of people it doesn't. There will be another writing assignment this week. I'll change the due date for the Desmos thing. Change it for like next week. So you'll have two of them due. But the Desmos thing's easy once you can log in. I guess the hardest part is just logging in, right? All right, so this week, this module has 4 homework assignments in it. I think they should have put some of this last week, but hopefully they're not all long. Okay. I mean, I don't think they would be. I mean, your homework assignment from last week was only 8 problems, right? It's not much work at all. So even if you have 4 homework assignments, 8 problems each, it's still only like 32 problems. I have a whole week to do 32 math problems. We can do that. Exponential functions. Y'all are familiar with exponential functions. Y'all seen them in elementary algebra and then algebra and so on. So here's a quick recap, like 2 to the x, that's an exponential function. This is 2 to the 0, 2 to the first, 2 squared, 2 cubed. You can see that this thing blows up real quick. At 0, you're going through 1. So exponential functions all go through the point 0, 1, and they look like this. So when you go to the right, they get bigger and bigger. If you go to the left, think about it, 2 to the minus 1, that's a half. 2 to the minus 2, that's a fourth. 2 to the minus whatever. It gets closer and closer to 0 when you go to the left. It's never equal to 0. It just gets closer and closer to 0. Compare that to something that's linear of slope 2, right? Every time I'm just adding 2. Sure, it increases, but it's going to look more like that, right? Just a straight line. So sometimes these are bigger than these in the short run, but exponential functions grow fast exponentially. If you make the x negative, so 2 to the minus x, right, that would be a flip over the y-axis. That would just take this dude and it would flip it like this. So you would end up with exponential decay. As you go to the right, you plug bigger numbers in for x. 2 to the negative big number is 1 over 2, right? This is 1 over 2 to the x. So that would give you exponential decay. Here's a better picture of an exponential function. Boom. Okay. So if let's say you had 3 to the x, it would grow a little bit faster and decay faster. If you had say if you had 1.5 to the x, right, it would grow a little bit slower. But all your exponential functions are going to look like this. Basically, they're all going to look like that. They're all going to go through this point right here, 0, 1. And that's because b to the 0 is 1. Okay. So your basic setup for an exponential function, I'll call it int x, is a b to the x. Okay. So you have this, which, remember your trig functions, the a was the amplitude, right? You know what this is? This just stretches your function vertically. Okay. You can also, of course, add something which would shift the exponential function up and down, or you could subtract something from your x, and that would be a shift to the right. Right, just like your trig functions, you can do all that. We're only concerned with a and b in here, okay, for now. So notice that you plug in 0 for x, this is just 1. So they call a your starting point. Starting point. And that's because if you plug in 0 here, this goes away and you just get a. Okay. So that's useful knowledge. Here's the basic properties of exponential functions. Okay, and here's something to note. Your exponential function here, b needs to be a positive real number, but it can't be 1, because 1 to the x is just 1, right? That would be a horizontal line, right? That'd be the constant function 1. So b needs to be a positive number, but not 1. Why does it need to be positive? Well, think about negative 2 to the x, right? This is a negative number, right? If x is 1/2, you're getting the square root of a negative number, right? And then we're in the realm of complex numbers, right? So your b here, your base, always needs to be a positive number, okay? Does that make sense? Yeah, because you don't want to, otherwise you're in the realm of complex analysis, all right? And a can be anything you want it to be, basically. The domain is all real numbers, because this thing goes infinitely far to the right and infinitely far to the left. The range, it goes up to infinity. It goes down to 0 with the round bracket here, because this thing never touches the x-axis. It just gets closer and closer and closer. All right, so it's never actually equal to 0. All right, if you go to the right, this thing blows up to infinity. If I go to the left, it gets closer to 0. And it will never touch the x-axis, right? Think about this. This is never equal to 0. There's no x you can plug in that's going to give you 0 there. And then y equals 0 is a horizontal asymptote, meaning right here, right? This thing gets closer and closer to 0, never touches it. That means horizontal asymptote. So there's your basic properties. Paste this in here. Here's a reiteration of the definition here. So the a is a non-zero real number called the initial value or starting point. B is any positive real number, but not 1. The domain is all real numbers. The range is all positive real numbers, unless a is negative. A is negative, then you're down here instead of up here. You saw that better. Yeah. If a is negative, you just flip. Okay. And then let's look and see if we can identify some exponential functions here. So which one of these are exponential? The x is in the exponent. Boom. This one, the x is not in the exponent. It's not exponential. It's a polynomial, right? This one, the x is in the exponent, right? This one, the x is in the exponent, but our b here is negative. So that's going to give you a complex valued function, right? So that one, even though the x is in the exponent, the b is not an element of the positive real number. And more examples. All right, this is a polynomial, or no. This one, the x is in the exponent, and this number is a positive number, not equal to 1, so that one's good. This is linear, right? It's just a line with slope 1.75. This dude here, this number is a positive real number, and then the x is in the exponent. Just because that's minus, that's okay. All that did was flip it over the y-axis. So instead of looking like this, that dude's going to look like this. It's exponential decay. Evaluating exponential functions, you all know how to graph, right? Usually you're going to need a calculator, right? Except for like fancy, easy numbers. So here's a exponential function. What is f of 2? Well, we replace the x with a 2. All right, so this is 5, 3 cubed is 27, and whatever, 5 times 27, all right? Use the calculator. And here's another exponential function. We want f of 3. All right, we replace x with 3. This is 8 times 1.2 to the negative 2 power, or 8 divided by 1.2 squared. This is whatever, plug it in your calculator, all right? So it's easier with these whole numbers here, that like what is 3 to the 3.1415 power? Right? I don't know. Plug into your calculator. There's a button for that. There's a button called x to the y. You want to figure that out, right? Okay. Here we're talking about exponential growth. The most popular example is population. Population grows exponentially. All right. They say A is the initial or starting value. That's because, again, f of 0 would be A times b to the 0, just A. Okay. B is called the growth factor, or the growth multiplier per unit x, meaning every time I add 1 to x, I'm multiplying by b again, right? So the difference between b to the first versus b squared is I'm multiplying by b. Every time x goes up by 1, the y value gets multiplied by b. Okay? There's an example for stores. So company A has 100 stores and expands by opening 50 new stores a year. So here's the years. You start off with 100 and then add 50 each year. Boom, 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 boom. So that's going to be linear, right? Versus company B has 100 stores and increases the number of stores by 50% per year. So this is its growth function, right? You start off with 100, then you're adding 50%, adding 50%. You might see this as the amount is principal times 1 plus the rate to the time. That's your simple interest formula, right? Y'all remember that? So exponential functions are used in all your finances a lot, right, because of compound interest. So you can see here the graphs of these two functions. They both start off at 100, right? But the exponential one, right in here, you can kind of see the exponential is less than the linear one, but if by the time you get this far, right, the exponential overtakes the linear. At the beginning of this section, the population of India was about 1.25 billion in the year 2013, with an annual growth of 1.2%, or 0.012. Situation is represented by the growth function population. Here's your A, right? 1.25 billion. That's the starting point. We're calling year 2013 year 0. All right. That's used the number of years since 2013. To the nearest 1,000, what would the population of India be in 2031? Well, if this is times 0, let's see, 2033 would be times 20, so this is times 18. The population 18 years after 2013 would be 1.25 times 1.012 to the 18th power. Okay, and plug that in your calculator and round. Y'all know how to do that, right? The hardest part of this section is going to be typing stuff into your calculator correctly. All right. This one's going to be exactly the same as the last one. So, how to find an exponential function given data? Instead of reading this paragraph to you, let's just look at an example. We need 2 data points, right? Here they say n of t. We're going to call our function n of t. And they say it's exponential, right? An exponential function. So it has to look like this, all right? T's are variable. So to figure out the formula, we need to find a and b. So we need 2 equations relating a and b because there's 2 unknowns, a and b. So if we have 2 data points, meaning just 2 points on the graph, that'll give us 2 equations and we can solve for a and b. So they say in 2006, we'll call this year 0. There were 80 deer. So we know that the population at year 0 is 80. All right. And then in 2012, let's see, that would be 6 years later, the population is 180. So this is basically 2 points on the graph. They're saying here that 0, 80 is a point on the graph, and over here they're saying that 6, 180 is a point on the graph, and then they say it's an exponential function. So we have 3 pieces of information. This tells us what the graph looks like, and then this gives us 2 points on the graph. All right, but we know our function needs to look like a times b. In this case, this is when t is 0. So this is just a times, because this is just 1, right? So we already see right here that a is 80. So we know that this needs to look like 80 b to the t. We just need to know what b is now, right? Well, we have this piece of information. If this is n of 6, then we know that a is 80. This would be 80 b to the 6th. All right, so all I did was plug in what we know about a. This is what n of t looks like. We need to figure out what b is. So we would have b to the 6th is 180 over 80, or 18 over 8. So b would be the 6th root of 18 over 8. Right, and you could approximate this to a decimal, but I don't recommend it, okay? Here's why. All right, here's n of t. We know a is 80. We know b is 18 over 8 to the 1/6. This is 80, 18 over 8 to the x over 6. Right? If I turn that into a decimal, right? Even if I rounded it to the thousandth place, right? This is an exponential. Think of the difference between 3.145 and 3.146. Those are really close, right? But raise them to the 2000th power. You see, every time your x increases by 1, you're multiplying by this number. So even though you're off by 1,000 here, take that 1,000 and multiply it by itself 2,000 times. You're going to be way, way off, aren't you? Right? Because that rounding error is going to get compounded over and over and over and over and over again. So that's why it's important, when possible, you want an exact value here. All right. There's other times when it's less important. This is one of the times that it's pretty important. Okay. So I hear that WebWorks sometimes it'll tell you to round, but it won't accept the answer unless you put in an exact answer. Right. So just put in the exact answer. Right. It just requires you to know your basic math more, instead of just typing something in the calculator. It makes you simplify fractions and simplify square roots and stuff like that. So aim for exact numbers. course, I could simplify this, right? 18 over 8, I could simplify that as a fraction, right? But still, it's exact. Might not be in simplest form, but it's an exact number. That was that one. Try it number 4, okay. All right, a wolf population is growing exponentially. Okay, so we know our population looks like this. That's what that says. In 2011, 129 wolves were counted. So if I call that times 0, this is saying that in year 0, we had 129 wolves. Right off the bat, I know that this is A times B to the 0, which is just A. So I already know A is 129. So whenever they give you the value at times 0, that automatically gives you your A value. So I know that this is 129 B to the T. Okay. Now they tell me in 2013, let's see, that's 2 years later, right? 2 years later, the population is 236, right? And this is N of T. Well, I know A is 129. This is B squared. All right, so looking at this, I could see, oh, obviously B is the square root of 236 over 129, right? Or 236 over 129 to the 1/2 power. That means N of T, A is 129, and we got 236 over 129 to the 1/2 to the X, which I could write as X over 2, okay? And I'd leave it like that. You might try to like combine these, don't do that. Then you end up with different powers of X on the top and the bottom of the fraction, okay? All right, now, bit of a word problem. Is just straight math with no context. The only thing that makes this is a little different is they don't tell you this point, 0A. They don't tell you the initial point. They give you 2 other random points, right? And that's okay. Again, we want to say N of X is A times B to the X. I'm just going to use N because that's what we used in the last example to name the function. So this right here says that N of 1 is 3, and this one says that N of 2 is 4.5, right? Well, this is A times B to the first, and this would be A times B squared, right? So we have 2 equations, 2 unknowns. How do we solve? Well, this one right here makes it real easy. We could say, okay, obviously A is 3 divided by B. I'll write it like that, okay? And then we substitute that into this equation, and then we only have B's and we can solve. Y'all remember how to solve systems of linear equations, two variables, you substitute one into the other. If I plug that in here, I'm getting 3b to the minus 1 times b squared, which is just 3b. So 3b is equal to 4.5, then b is 4.5 over 3. So now that I know my A and B, let's see, I don't know A and B yet. This is B. A is 3 times that, so this is 3, 4.5 over 3, the minus 1. So this would be what, 3 times 3. This is 9 over 4.5. I did my arithmetic right. So that's the A value. Because once I found B, I plugged it in. Now I have A. So this is 9 over 4.5. And then B is 4.5 over 3. And then we need the X value, which we could simplify this a little bit, right? Let's see. 9 is 3 squared. And then we have 4.5 to the X. And we have, we're dividing by 4.5, right? So this is 4.5 minus 1. And then this is 3 to the minus 1. let's see if we can simplify this stuff. We need everything to the x minus 1. So I have 3 times, let's see, this and this gives me a 3, right? Oh, wait. This is minus 1. This is to the minus x. Right, to the negative x. How could we do this? This is 4.5 to the x minus 1. And then let's write this. This is 3 to the first times 3 to the first and 3 to the minus x. And then this is 4.5 to the x minus 1. Yeah, I'm just going to leave it like that. We're messing it all up. There is a way to write this to make it prettier. All right. Yes. Yeah, I think. Oh, yeah, that's even better, too. Yeah. This is 2. The obvious that I wasn't recognizing. I was trying to meld this into here and adjust the x, right? Well, you don't have to do that. It's a lot better. 2 times 4.5 over 3 to the x power. Thank you. And A is 2. Okay. Do 2 points always determine an exponential function? Well, if you know it's exponential, you can find a unique exponential function to go through it. Yes, provided the 2 points are either both above the x-axis, so they're both up here, or they're both down here. But if you have one up here and one down here, you can't do that because exponentials don't cross the x-axis, right? Not every graph that looks exponential really is exponential. We need to know the graph is based on a model that shows the same percent growth with each unit increase in x, in which many real-world cases involves time. You'll see, like in higher level physics and stuff, you probably see it elsewhere. If you have data, you look at past data and you see, oh, this looks like it fits an exponential graph. And maybe all the data that you have from the past fits an exponential graph perfectly. But that doesn't mean that in the future it's still going to be exponential. All right. So if you're trying to predict the future, you try to model stuff mathematically and you're like, this fits an exponential function perfectly. But there are other functions that look just like exponential functions, but for higher values of x, they're not. So if you're trying to make mathematical models, it's like, how do you differentiate? Well, sometimes you can't. Sometimes you just have to wait and get more data from the future to see, is this thing deviating from an exponential function, right? Or you have to dig into the past, try to find even more data, but really the deviation will come in the future, right? So even though all your data fits exponential and you can keep looking in the past, getting more data and it all fits exponential, doesn't mean that in the future it's still going to be exponential, okay? Because there's other functions that look just like exponential, but in large values of x, they start to deviate, okay? There's a big area of study just for that issue. Yeah, we did that one. We did that. How to. All right, now we want to look at a graph and be able to figure out the function. This is the same thing we just did, but instead of them telling us 2 points and us figuring out the function, we look at the graph and we figure out 2 points. The best point to always look at is that one right there. That is 0, 3, right? So we know our function n of x, which is a times b to the x. This tells us that n of 0, a times b to the 0, which is a, is 3. So if you get that point, you automatically know your a value, right? A is 3, it's your starting point. So now we just have to figure out what b is. Pick any other point, all right? They say that if you can pick a point real far away, that helps. In this case, the second best, to find your b, look at 1 here, right here at 1. Luckily, this is easy to see that it's 6. We see that n of 1 is equal to 6, right? The reason why that one makes it easy to find b is because this would be, let's see, a is 3, and then we have b to the 6th power. So this tells us that b to the 6th is 6 divided by 3. So b is 2 to the 1/6 power. So that tells us n of t, a is 3, b is 2 to the 1/6, which we could write as 2 to the x over 6. Okay. So you just need 2 points, right? The convenient one is right here at n of 1. You can find out what that output is. Okay. So it's not too hard. Let's look at another one here. So here they say, you might not be able to read that. That's root 2. So you can look at this right off the bat and say, oh, a is root 2, right? That's your starting point. So we need to find b. Okay, well, n of x is going to be root 2 b to the x. Let's find another point here. Something, maybe this one. We could see that n of 3 is equal to 4, right? And that would work, but I like this one right here better. That n of 1 is equal to 2. So this would be root 2 times 2 b to the, dang it, to the first, right? There's our x. So we're just replacing the x with a 1. So having this, we see that, okay, the reason why I like 1 here is because you get b to the first, which is just b, right? That's the only reason why. So I got 2 over root 2. 2 is root 2 times root 2. So 2 over root 2 is just root 2. So b is root 2, a is root 2. So our function here is root 2 times root 2 to the x. Well, root 2 is 2 to the 1/2, and then we have 2 to the 1/2 to the x. So 2 to the 1/2 times 2 to the x over 2. And since these are like bases, I could say this is just 2 to the 1/2 times x plus 1, right? It's x over 2 plus 1/2, x over 2 plus 1/2. So that's how I would write this. 1/2 times x plus 1 is the exponent. You don't even have an a value. Okay? I mean, or you could write it like this. These are both the same thing. So there's your starting point, right? If you write it like this, there's no a. It's because we've shifted this thing to the left. If you take this guy and you shift it to the left, it's going to change your a value, isn't it? So your starting point. Okay? So this is prettier, but this has its own privileges, again, because you can just look at that and see that's the starting point. If you write it like this, you can't see what the starting point is. Okay. Use a graphing calculator. I'm not going to do this. Use a graphing calculator. How would you use a graphing calculator? We see that, well, n of 2 is 24.8 and n of 5 is 198.4. I don't know how we'd use a graphing calculator to do this. Let's see. This is a times b squared, and this is a times b to the 5th. We have 2 equations, 2 unknowns. This tells us that a is 24.8 b to the minus 2. If we substitute that in right here, 24.8 b to the minus 2 times b to the 5th would be b to the minus 3. So we'd have b to the minus 3 is 198 divided by 4 over 24.8. So b would be the cube root of 24.8 over 198.4. Plug that in here. So A is 44.8. This to the minus 2. Okay, that's going to be the cube root of, now let's do this. This is 198.4 over 24.8. That I flipped it over to deal with the minus. So then we have squared, the 1/3, so 2/3. So there's your A value, and here's your B value. I don't know how you use a graphing calculator to figure that out. We could just do the basic math, right? It's the same process we just did, but with ugly numbers. Okay. Here is, I don't know, I had a calculator, but it pissed me off, so I stomped it to pieces. So you could say press stat and whatever. I guess if you, I don't know, this is bullshit. I'm not going to go with this. Use a computer. Don't use a graphing calculator. This isn't 1980. Okay? But apparently, every piece of software is going to be a little different. I mean, every software program, you can enter in points on a graph, right? And then it'll try to figure out what the actual function is. Okay? So it's going to be different commands, different things you're going to click on. So I'm going to stop there today. I'm not going to cover this graphing calculator nonsense. Next time we will do compound interest, which I assume y'all have seen compound interest before. All right, it's not hard. The hardest part is plugging it into your calculator correctly. You didn't mess that up. All right, let's get out of here.